Alright guys, this should be our last video here on our AP Calculus Final. We're looking at calculator questions number 7 through, I think this goes to 11. Okay, so 7 through 13, that's fine. We have a radioactive element has a half-life of 50 days. What percentage of the original sample is left after 60 days? So I'm going to start off with just the regular equation for decay and growth, exponential decay and growth. And I'm going to pretend I don't remember how to use the half-life formula. If you do know how to use the half-life formula, then this becomes a little bit on the easier side. So by definition of half-lives over here, the amount of radioactive element at 50 days, the equation is going to be equal to P naught e to the 50k. We've substituted t with 50. And then since it's half-life, the amount that we're going to have is half of the initial amount, or 0.5 of P naught. Now I know this is a calculator problem, so you're probably itching to use your calculator. I want you to notice that the P naughts in this equation can actually be divided out. And we now have an equation which is really going to be good for us to put into our calculator. So let's get to our calculator, which should be still in, well, no, that's kind of weird. We're going to take this into our solver. And yeah, we have nothing in our solver. Let's get started with putting stuff in here. I'm going to put P on the right side. On the left side, I can't use P again, so a lot of people have taken to using O there for P naught. And then we're going to put E to the KT. And we'll just go ahead and solve this. Now, if we're solving this, the P on the right side, as it turns out, is going to be equal to 0.5 right over here. So let's put 0.5 here. O, in this case, is going to be 1 since it doesn't appear in our equation. And T is going to be, how much is that, 50? 50. Now we're going to solve for K. Now I would not recommend you solve for K starting to look at 0 because we know the K is going to be a positive amount. So I'm just going to put a 1 here. Starting at 0 sometimes gives you a problem. Let's do an asymptote here at 0 with the equation. So alpha, enter. That's going to be a value for K. Yep, it does. It's negative 0.0136. With my value of K, I'm now ready to complete this problem. So let's write down exactly what the equation that we're going to be solving is. So putting in our 60 and our K, that doesn't really, well, no, it helps, but what happens here is we don't have an initial amount. So this has to equal something. And if I want to know what percentage is left, usually a wise choice for P naught would be 100. That means whatever comes out here is going to be the percentage. So I'm going to put this into my calculator. We'll make our original amount 100. And then we'll we'll change T to 60. And then we'll solve for P. And that's going to give us 43.527. And that gives us that 43.537% is left. And the other side of the coin is that 56.463% has decayed. That's how much has already been transformed. Number 8 is a problem which is, well, this looks to me like a partial fractions problem. If we take this and equate them, we should be able to solve for a and b. The first thing to do is to put everything to a common denominator. To do that, we'll multiply the first partial fraction by x minus 5 over x minus 5. I mean x plus 5 over x plus 5. And then we'll multiply that second partial fraction by x minus 3 over x minus 3. And you'll notice that the denominators here will all match. This is equal to this, which is equal to this. So if all the denominators match, well, no, let's do this. Let's simplify this a bit. Okay, so we have everything in common denominators. And if everything has a common denominator, that means all the numerators have to equate as well. So in other words, x plus 1 has to equal a x plus 5 plus b x minus 3. Since this is a review, I'm just going to go ahead and do what we need to do to solve this. The first thing to do is consider what happens when x is equal to 3. If we consider that, then 3 plus 1 has to equal a multiplied by 3 plus 8 plus b multiplied by 3 minus 3. This simplifies into 4 is equal to 8a, and therefore a has to equal 1/2. Now we're going to do this again for the next value here, which would be x equals -5. Substituting in -5, we get that -5 plus 1 is equal to a multiplied by -5 plus 5 plus b multiplied by -5 minus 3. This simplifies into -4 equals -8b, and therefore b is also equal to 1/2. So I think that's all we needed to do here. We needed to find a value for a and b. I'm going to let this one rest and move on to question 9. The spread of a virulent flu in a certain school on Oahu's north side is modeled by the differential equation below, where t is a number of days after the students are first exposed to the infected student or students. Estimate the number of days it will take for a total of 125 students to be infected if 2 students are initially infected. Round your answer to the nearest day. Okay, looking at this differential equation, this looks like a disguised form of the logistic differential equation. Looking at this further, if that's it, this right here, 0.00657, that's going to be my value of k. And then over here, 1.05, that's my value of m times k. So let's take this and let's factor. So I already know that I'm going to be factoring out a p, so I'm going to change that p squared into p times p. If I do the division, I get that 1.005 is 150 multiplied by 0.0067. So we're going to factor out this 0.0067p. And that makes this look a lot like kp multiplied by m minus p. So I know that k is equal to 0.0067, m is equal to 150, and as a bonus, k times m is equal to 1.005. So once we verified that we're working with a logistic differential equation, we pull out our general equation for the general solution for the logistic differential equation. And then we start substituting our values. And now I can start working with my calculator. You know, I love putting the entire differential equation or the entire solution equation here with all the parameters intact. I feel like it gives me a lot more control over what I'm putting into my equations. So I'm going to substitute things. Let's see, we know M, we know K, and we know that when T is equal to 0, there were 2 students infected. Now this is enough information for me to solve for A, which I'll push alpha enter, and we'll get a result. There we go. A is pretty much 74, which we can go ahead and write into our equation here. And now we can write the same equation and say we want to know when the amount of people, P, is equal to 125, and we're going to solve for T now. Over here on the solver, we know we want P to be 125. M is the same, A is going to be the same, K is going to be the same. We just need a value for T. I don't like starting with 0, you should know that. So I'm just going to put a number here. A positive number is what I should be putting in. The exact value doesn't really matter. And from here, I'll push alpha enter. And that should give me a T of 5.88. And lastly, it says to round the answer to the nearest day. So after 6 days, there will be 125 students infected. That is a very virulent flu. Let's move on to number 10 here. We have a car moving with initial velocity of 5 miles an hour accelerates at a rate of AT equals 2.4 t miles per hour for 8 seconds. How fast is a car going when the 8 seconds are up? Okay, so our first fact to know is that the velocity, the derivative of velocity, is going to be equal to acceleration. So this says to me that the integral from a to b of the acceleration is going to be vb minus va. We know the initial velocity is 5, so that says I should use I should use 0 for a. Secondly, we want to know how fast a car is going when the 8 seconds are up. So if I want to do 8, I'm going to have to change b into 8. Again, I know that the initial velocity is 5 miles an hour, so I'm going to substitute 5 for v0. And the last thing I'm going to do here is I'm going to put 2.4 t for the acceleration function. Okay, that's not the last thing I'm going to do. I'm going to solve for the velocity at 8. So this here, what we just went through, this is me using the fundamental theorem of calculus. So you have to do a lot more than just take the integral of the acceleration function in order to get the velocity. You've got to use the fundamental theorem. Now, we're going to do this with our calculator. We'll get to the home screen and these functions are easy enough. So I'll just put 5 plus the integral from 0 to 8, 2.4x dx. 5 plus the integral from 0 to 8 of 2.4x dx. And that gives me 81.8. And that's going to take care of it for question 10. Let's take a look at number 11. Number 11 says to find the area in the first quadrant bound on the left by y equals x, bound above by y equals 1, and bound on the right by 1/4 x squared. I'm going to put those functions into my calculator in the y equals menu. I'm going to push window. And the question says I'm only looking in the first quadrant, so I'll change the x min and the y min to 0. Then I'm going to push the graph button just to see that region. So that's the left boundary. The next one is going to be the above boundary. And the next one's going to be the right boundary. Okay, so we're talking about this region right over here. Let's zoom in on that. And for that closer zoom, I'm going to use the zoom box. Okay, I'll get my cursor over in the bottom right-hand corner. Then I'll push enter and I'll start dragging my box so that I have my interesting region here into my calculator, or into that box. Push enter to zoom into that box. Now I'm looking at this region, and this, since the blue line is y equals x and the red line is y equals 1, where they intersect, y has got to be equal to 1. And if y is equal to 1 and we're on the blue line, then the x coordinate is 1. So I'm pretty sure that if I trace along and I go to x equals 1, that should get me right at that intersection. Now the other intersection on the right over here, that looks like it's close to, what is that, 1.9? So we'll go to 1.9 and we'll see. Yeah, that's a little bit more than 1.9. I don't actually know what this intersection is. So I'm going to go and I'm going to find that using second calc and then intersect, which is number 5. It's going to ask me, first of all, am I on the first curve? And let's see, the first curve is not the blue curve. The first curve is, yeah, the red curve is going to intersect the black curve. So I'm on the red curve right now. I'll push enter. Next one says, am I on the second curve? And yes, this black curve is the other curve that's going to intersect. And then it says to guess, so I'm going to move the cursor close to the point of intersection. May have gone a little bit too far. I'll push enter. And that is my value when x equals 2 and y equals 1. So this is really nice. Let's copy this screen. Now we've got a couple of strategies on how to do this, and I'm going to go over both of them. The first one strategy is to look at this top to bottom curve. Now in this yellow region, the top curve is the blue curve, and the bottom curve is the black curve. So this yellow area is the integral from 0 to 1 of the blue curve minus the black curve. And the second area that I want to consider is going to be this one that I'm drawing in blue, and that's going to be the red curve minus the black curve. Remember, the area of the blue one is going to be the integral from 1 to 2 of the red curve, which is 1, minus the black curve, which was still 1/4 x squared dx. Remember, every time we change either the top curve or the bottom curve, we're going to have to set up a new integral. Now the total area is going to be those two areas added together. So let's go ahead and get that to the calculator. Let's make a note that y equals x is the blue curve, which is y1. Y equals 1 is the red curve, which is y2. And y equals 1/4 x is y3. So when I go to the home screen, I can just put those together. So this is the integral from 0 to 1 of y1 minus y3. Y1 was y equals x. Y3 is y equals 1/4 x to the second power. And we're going to add to that to the integral from 1 to 2. And this time it's going to be y2 minus y3 dx. Push enter and that will give me a result. If you need to turn that into a fraction, of course, you can use the fraction and get 5/6. So that was strategy 1. Strategy 2 is to consider this sideways. So we are going to do the right curve minus the left curve. So we're going to do the right curve minus the left curve. We notice that the right curve is this curve y equals 1/4 x squared. Okay, well, I can't actually use that. I have to solve for x in this case. I need a function in terms of y. That equation solves nicely into x squared equals 4y, or x is equal to the square root of 4y. I would not recommend simplifying it much more than that. You're going to have your calculator with you, so there's no real point in simplifying that. Now, the left curve, well, the left curve is this blue curve, and this blue curve has the equation y equals x, which simplifies nicely into x equals y. Actually, that's exactly the same equation. So now that we have a right curve and a left curve, all we need is a y minimum and a y maximum. And I think you can see that a y minimum would be down over here, and that's at y equals 0. And then the y maximum is up here, and that is at y equals 1. Putting this together, we have the area is y min to y max of the left curve minus the right curve dy. We already talked about the y min and y max. And I have the left curve and right curve backwards. Sorry about that. It should be right curve minus left curve, not left curve minus the right curve. I'm sure you were scratching your head there for a minute. Okay, the right curve is root 4y, and the left curve is just y. And now the only thing left to do is to put this in my calculator. So we're going to integrate from 0 to 1, square root of 4y. And by the way, you can just put a y into the calculator like that, minus y, and we're going to do dy, and that gives me the exact same result. So either of those strategies work. Doesn't really matter which one you use. Let's move on to question 12. Find the area of the shaded region that's bounded by the curves f of x and g of x. So let's graph this so we can find out what this region looks like. We'll put the functions into our calculator. And since we don't really know what zoom to use, we're going to use zoom 6, which is zoom standard. And let's see if we can find a region. Okay, so there are actually two regions here. This region here goes from, it looks like about 2-ish to 0, and the second region goes from about 0 to about 2. We're going to have to find all of those intersections just to make sure. So let's second calculate. First intersection, number 5. So it's an intersection between the blue curve and the red curve. It's right around x equals 2. So yeah, that first one is x equals 2. Let's find the next one. That looks like around x equals 0. So we have blue curve, red curve. We're going to guess 0. And yes, it is 0. So this first one is from 0 to 2. Now what about this last one over here on the left? Let's calculate an intersection again, number 5. Blue curve, red curve. And this time our guess is going to be -2. And it actually is -2 where those curves intersect. So strategy is we're going to, well, let's copy and paste this function. We're going to divide this into two regions because the top curve changes from red to blue. So we're going to do this first region right over here, the yellow one. So our first area is going to be the integral from -2 to 0 of g of x minus f of x, remembering that g of x is the cubic function, and the cubic function is the same as the red function. Now the second area that we're going to look at is going to be this blue area right here. And in the blue area, the quadratic function is on top and the cubic function's on bottom. So for the blue area, it's the area from 0 to 2 of f of x, which is the quadratic, minus g of x, which is the cubic. So let's figure out which one is which on the calculator. We want to know which one is the cubic because that's going to be g of x. And if I go to y equals, it looks like g of x is going to be in y2. On the home screen, we're going to now integrate from -2 to 0. And the cubic is on top, and the cubic is y2. So we'll do y2 minus the quadratic, and the quadratic is in y1 dx. To that, we're going to add the integral from 0 to 2. And this time we're going to do the quadratic, which was in y1, minus the cubic, which was in y2 dx. And that should give us the result of 16. We'll just leave a couple of calculator notes, and we are on to the very last problem of this final review. Yes, number 13. Find the area enclosed by the lines and curves. So this one, I noticed that I have a square for the y. I have a y squared, and I don't like that very much. So I'm going to transpose this. I'm going to reflect this. Is a technical thing that's going on. So here we have x squared equals 4y plus 4, and x equals 4y minus 16. Now we have to solve for y. Now that I've solved for y, I'm going to put these two functions into my calculator so I can see which region we're talking about. Again, I'm going to push zoom 6, zoom standard, because I'm not sure how this is going to look. All right, that actually looks pretty decent. It's going to be y2 minus y1 in this region here, because I have the linear on top of the quadratic. I should find these points of intersection with my calculator. So blue curve, red curve, push enter. Next one is a guess. This guess looks like it's about -1, 2, 3, 4, right around -4. And yes, it is -4. Next, we'll find the intersection on the right side by calculate intersect. First curve is blue, second curve is red. Take a guess. That looks like around 1, 2, 3, 4. It looks like around 5 actually. So we'll put a 5 in there, and it actually is 5. So we're going to integrate from -4 to 5. Writing down an integral, we can see that our limits are going to be -4 to 5, which corresponds to the x-coordinate here and the x-coordinate there on the right side. 1/4 of x plus 4, that's the linear function in red over here. And then 1/4 of x squared minus 1, that's this quadratic function over here. So the top function is linear, the bottom function is quadratic. On the calculator, I'll integrate from -4 to 5. Let's make sure the linear, the linear is in y2. So we're going to do y2 minus y1 dx. And that gets me 30.375. And if I wanted to turn that into a fraction, of course, hit the fraction button, and that gives me 243/8. And folks, that's going to do it with our AP Calculus final review. I wish you all the best of luck, and we'll see you next semester for AP Calculus C. Have a good winter break, everyone.